Hello, this is lecture 3 of our linear algebra series. So let us quickly recall what we have last time. We have direct sums and subspaces first, and then we go to sums and direct sums. We define a subspace, and then we have a special subspace, the sum, and then the direct sum. And then we introduce the notion of independence, linear independence and linear dependence. And then associated with that is spanning list or spanning set. And then with spanning set, we have finite dimensional vector space. So they are basically vector spaces spanned by a finite number of a finite list or a list of finite length. When I say length, the number of elements in the list. So today we will have the notion of basis first, dimension, and we will end with linear maps. Let us start. So what is a basis? So last time we have the notion of linear independence, and then we have the notion of a spanning list or a spanning set. Now we define basis. A basis is basis of our, here V is again a vector space, is a list or a set in some books, is a list of vectors in V. That is the first requirement, linearly independent. And the second requirement is spans our vector space V. So to illustrate bases, we have what we call examples of bases. So the list of one as our first component, and then the second one in the second component, and zero all else. And then the third is zero, and then zero, and then one in the third, and so on. End with zero, and then one at the end component is basis of our f to the n. Of course, our f to the n is again either r or c. So this basis is this is called standard basis, or sometimes canonical basis of our f to the n. Some standard basis. The other non-standard basis, of course, if you have R3, 1, 0, 0, 0, 0, 1, and then I forgot the second one, is a basis of our F3. Now, recall that I have hidden parentheses here, but by convention, we have set that as this is just a list, and then this list has no parentheses, and this is understood to be some set here. Another one is the following. I will leave the checking 1 and 2, and here 3 and 5 is a basis for or of F2. Note that 1, 2 here is not linearly dependent, or is not a scalar multiple of 3, 5. Considering F2 being R or C. Okay. So we cannot multiply 1 comma 2 with some real number so that it will give us 3 comma 5. Okay, we can find that. And lambda such that lambda 1/2, a lambda 1 comma 2 is equal to the ordered pair 3, 5. All right. So let me have the list 1, z squared, and then up to z to the m is a basis for our polynomials of over f of degree at most m. Recall this example from last time. So now we will have some criterion for basis. Let me state this as a theorem, criterion or basis criterion. So this is just a theorem which determine another, basis is a spanning set, and then it is also a minimal spanning set. Here is another definition of a basis. So the least V1 to Vn of elements of V, the least is a basis if and only if for every V in the vector space B, V is just a scalar combination or a linear combination. V can be written uniquely as A1 V1 plus up to AN Vn, where A1 here up to AN are elements of F. So the proof here is procedural and I think easy. So let me just say the first part. So first is we assume that V1 to Vn basis. Then what? Um, the step is to show, let us consider AN Vn and Cn Vn be representation of our V, show that our A1 is AN is equal to Vn for all n. Okay. Okay. Let me change the subscript here because I, and then for all I from 1 up to n. So here I. So how do you show that? Suppose these are two representations, and then we subtract one from the other, we get 0. We get 0 is equal to A1 minus C1 V1 up to AN minus CN, and then Vn. Then since our V1 to Vn is linearly independent by linear independence of V1 Vn, we get AI minus Ci equal to 0, which gives us AI equal to Ci for all I index. Okay, so the first part is something like that. Just like that, just write it properly. The second direction is, suppose that every vector can be written uniquely as above. Then how do we show that this this is linearly independent? This is basically because of unique representation of our suppose that we have a unique representation, then it will imply that this A1 to AN is 0, thus linearly independent. and hence a basis. Okay? Because clearly our V1 to Vn spans V. So the reverse direction is left and it's easy to figure out. Now, I will also have this remark. A spanning list in a vector space may not be a basis. So a spanning list may not be a basis. What's the issue? Because considering linear dependence. If the list is not linearly independent, then it's not a basis, but it's just a spanning list. Okay. Of course, but if we have a spanning list, I will state this as a theorem, spanning list, every spanning list can be reduced to a basis. So, of course, you just take a vector and vector 1, and then if 1 is 0, delete it, and then this the remaining is still spanning, and then inductively take another vector. If again the vector is the span in the span of the remaining vectors, just delete it. If the vector say v sub j is not in the span, leave it unchanged, and then proceed uh, uh, as usual. So from V1, if V1 is 0, delete it. If V1 is not 0, just let it be. And then for step, say J, if V sub J, so if, for example, the second vector is in the span, I mean, the V sub J is in the span of the remaining vectors, then delete V sub J from the list. If v sub j is not in the span, leave it unchanged, and then continue at v sub j plus 1. If it's again in the list, then delete it. If not, just continue. So by a repeated process, you get a collection of elements which are already linearly independent, because along the process, you have discarded vectors that are um, uh, linearly dependent with each other. So yeah. The next theorem is if we have a finite dimensional vector space, if we have a finite dimensional vector space, this always has a basis. Of course, the candidate for that is the canonical basis. And then the proof is, by definition, we get if the vector space is finite dimensional, then it is spanned by a finite list or a list of finite length. And then from previous result, the list of finite length can be reduced to a basis. As the previous, this theorem here. Finite dimensional vector space has a spanning list, which is of finite length. And by the theorem here, every spanning list can be reduced to a basis. How about if we have a linearly independent set? We know that a basis is linearly independent. But how about if we get a linearly independent set which is not a basis? The theorem says here that if we have every linearly independent set or list of vectors in a finite dimensional vector space can be extended to a basis. So how do you show that? How do you show that? So let us quickly write the outline of the proof. Suppose that U1 up to UM is linearly independent. Then in the vector space V, okay, we have let W1 to Wn be a basis. Be a basis. Now look at our U1 up to UM and then add to that W1 up to Wn. What can you say about this set? This is a spanning list for our vector space V. And then since this is a spanning list, by applying previous theorem, previous result, this has this can be reduced to basis, or this can be extended to a basis by adjoining elements of W1 to Wn, which is not linearly independent. And then, of course, it will contain what? It will contain U1 to UM. We will remove elements from W list until such time we get an element from a list from U1, including U1 to UM, adjoined with some elements from W1 to WN, which is already a spanning list, but linearly independent. Okay. So that's easy. And then lastly, to end this section, we have a theorem on direct sum. So every subspace of V is part of a direct sum equal to the space V. That is if U is a subspace of V, there exists a W subspace of V such that V is equal to U direct sum with W. I will leave the proof of this for reading. Now, we go to the definition of a dimension. So, this is just an easy definition to define any two bases of a finite dimensional vector space V have the same length. Okay, so let us, it's not a definition, it's a theorem. We will define a dimension later. So the proof is, suppose B1 is equal to, okay, B1 and B2 are bases for our vector space V. Okay? B1 is linearly independent in V, and B2 spans V. So the length, cardinality of B1 is less than or equal to the cardinality of B2. Interchanging role, we have B2 is also linearly independent in V, and B1 spans B. Thus, we have the cardinality or the length of B2 is strictly, you know that B2 here is linearly independent and B1 spans B. So we have B1, thus your cardinality of B1 is equal to the cardinality of B2. Okay, we say cardinality or the length if we are referring to the list, if we are referring to like a set of vectors or B1, then we can refer to it as the number of elements or the cardinality. Because if you consider the list that we consider as no repeating element. Okay, now we are ready to define dimension. So what is a dimension? A dimension is the dimension of V is the what? The length or the cardinality, the length of the bases of, not the bases of any bases. Always get wrong in spelling bases of V. And then we denote it by dim of V. So as example, we have the dimension or the dimension of Fn is equal to n. The dimension of polynomial at most n degree over the field F is equal to m plus 1. So basis here is 1, z, to zm, and then this is m elements, and then we get another 1 here. Okay, so yeah, that's it. We are doing things abstractly here. Now, another very obvious theorem, because of course, if your U is a subspace of V, subspace of V, and then we are considering only finite dimensional vector space, then the dimension of our U here is less than the dimension of our V. And then another theorem, every linearly independent list of vectors in V of length dim V and equal to the dimension of V is a basis of our vector space V. So this is an easy one. I leave the proof for you to verify. And for example, we have 5 and 7, and for 3 is a basis for or of F2. We don't need to, this list of vectors is linearly independent because we cannot find a non-zero scalar or non-zero element of F, so that we multiply 5, 7, we get 4, 3. Because the list has length 2 and the vector space F2 has dimension 2, then from previous theorem, our list 5, 7, and then the other is 4, 3. These two is a basis for F2. If we have a linearly independent list, the same is true. The same is true for a spanning list. If the cardinality of the spanning list B is equal to the dimension of V, then our B is a basis. Okay? Again, I will just leave the proof. And now we will go to the an important formula, which I will prove here. So this relates the basis or the dimension of the sum of two subspaces of a vector space. So let me write this as a theorem. If you have U1 and U2 subspaces of our V, and then V, of course, is finite dimensional, as I have mentioned earlier. We will just study finite dimensional vector space from now on. Then the dimension of the sum U1 plus U2 is equal to the dimension of U1 plus the dimension of U2 minus the dimension of the intersection of U1 and U2. So, okay, let me have a remark. It is an exercise that show that U1 and intersection U2 is a subspace of V. This is part of the take-home exercise. Now, let us prove this theorem. Not this theorem, but this theorem star here. Okay, let's start with with this is a relatively long proof. Suppose that U1, UM be a basis of our U1 intersection U2. And thus, your dimension of U1 intersection U2 is equal to M. Okay? Of course, this U1 to UM is linearly independent in U1, and also we can extend this to be linearly depend and this is U1 UM is linearly independent in U1. So extend to a basis of U1. So we get U1 to UM and then V1 up to say VJ basis of our U1. Okay. And then your dimension of our U1 is equal to M plus J. Also, uh, uh, consider extend to basis of U2. We get U1 up to UM, and then we get W1 to WK, and then the dimension of U2, this is a basis, a basis of U2. The dimension of U2 is M plus K. Okay? Okay. Now, we want to show that the dimension of U1 plus U2 is equal to M plus J plus K, which is just equal to M plus J and then plus M plus K minus M, which is equal to M dimension ng U1 plus dimension ng U2 minus dimension ng U1 intersection U2. So this is what we want to show here. All right, let us start the proof of our claim. This is the claim. We want to show this one is true. Let us start. So the span of our U1 up to UM, and then V1 up to VJ, and then W1 up to WK is contains U1 and then also contains U2. And hence equal to U1 plus U2. So to show that this is a basis, we need to show that this is linearly independent. So suppose that our A1, U1 up to AM, UM plus B1, V1 up to BJ, VJ plus C1, W1 up to CK, WK is 0. We need to show that the A's, the B's, and the C's are all equal to 0, where our AI, V, B, VLs, VL, and then C, Q are all in F. So here I, L, and Q are index set. And then we need to show that these are all 0. Okay? Now, we can rearrange this so that C1, W1 up to CK, WK is equal to the negative of A1, V1, U1 minus minus AM, UM minus B1, V1, and then minus BJ, VJ. Okay? Which shows, this shows thus your C1, W1 up to CK, WK is in U1. Since since our U1 up to UM, and then V1 up to Vj is a basis of U1. And also what? And then if we are going to have our all W's uh, are in U2. So we get C1W1 up to CKWK is an element of U1 intersection U2. This is an these ones are basis elements of U2. This one are basis elements of U U1. Because U1 to UM is a basis for we get C1W1 then plus CKWK is equal to D1 U1 plus DM UM. Here this is a basis for these W's are basis for um um U1, and then this U1 to UM is a basis for U1 intersection U2, where these are scalars. Now what? But your U1 up to UM and then W1 to WK is linearly independent. So what does it mean? Therefore, since they are linearly independent, we get our C's and D's are all 0. So if C's and D's are 0, this means that our A1 U1 plus AM UM plus B1 V1 plus BJ VJ is equal to 0. Because we have our C and D's are equal to 0, and then our original A, B, and C becomes this. Okay? Which implies that your U1 to UM and then V1 to VJ are linearly independent because wait, since okay, since independent, we get our A's and B's are 0. So from here, C's are 0. From here, A's and 0. A's are 0 and B's are 0. Thus, what? A's, B's, and C's are all 0. And that means, what does it mean? That means that this one, this long equation here, this long equation, let me highlight it in blue. This long equation here is linearly independent. And look at this. This one is the dimension of U1. And then plus U2. Okay. So I think I'll end the proof here. It's quite a long proof. This may be the one direction may came in the exam or an exercise. But yeah, that's it. That's the end part of our bases. Now we go to linear maps. This is chapter 3. Let us consider uh, our notation. Let us how F is our field. We get this is either C or R. Then V and W are vector space over F. And then, so that's our convention and notation. So we define a linear map. A linear map from our V to W is a function. Function I need. Hello. Sige, boy. Wait lang. Hello, do. Function T from V to W with some properties. Which I will discuss next recording. So I think that ends today's record.